Hi everyone, welcome to today's class. In the previous class, we discussed Gauss's law. So what was the statement of Gauss's law? The total electric flux passing through a closed surface is equal to 1 by epsilon 0 times the net charge enclosed by the surface. Okay. Today's class, we will discuss some applications of Gauss's law. So what was the statement once again? What was the statement for Gauss's law? The total electric flux passing through a closed surface is equal to 1 by epsilon 0 times the net charge enclosed by the surface. Epsilon 0 is the medium inside that closed surface. Okay, we have to put some charges inside a closed surface. Examples of closed surface: cuboid, spherical shell. Okay, so if you put some charges inside a closed surface, the total electric flux passing through it is 1 by epsilon 0 times the net charge enclosed by the surface. This was the statement. Today we will do some applications of this Gauss's law. There are mainly three applications for us. First one is to find the electric field intensity due to a uniformly charged infinitely long wire. Second is to find the electric field intensity due to a uniformly charged infinite plane sheet. Third is to find the electric field intensity due to a uniformly charged thin spherical shell. We discuss the first application. Number one. Electric field due to a uniformly charged thin wire. Okay, so let us consider an infinitely long, uniformly charged thin wire. The wire is very long. It is uniformly charged. It is thin. Let me draw the wire here. See, this is the wire. Okay, it is uniformly charged. Imagine Q, the charge on it. And let L be the length of the wire. Here I am defining a quantity called a linear charge density. Linear charge density is charge per unit length of the wire. I denote it by the letter lambda. Linear charge density denoted by the letter lambda. What is it? Charge by length. So we can write Q is equal to lambda into L. So linear charge density lambda Q by L. What is the SI unit of lambda? Charge by length. Charge unit is coulomb. Length unit is meter. So linear charge density unit is coulomb per meter. So this is the infinitely long straight wire, thin, uniformly charged. I have shown a small portion only. Imagine that it is infinitely long. Now we are going to find out the field, electric field intensity at this point near the wire. This point is at a distance r. Okay. We are finding the field up by applying Gauss's theorem. So we need a Gauss, we need a surface, closed surface. The wire has to be enclosed in a closed surface. So you imagine a cylindrical surface passing through this point. This is a cylindrical surface. Cylinder. The point P is on that surface. The surface of this cylinder is the Gaussian surface. Why we are imagining this cylinder? Because Gauss's law was applicable only for closed surfaces, right? We need to have a closed surface. Charges must be inside it. Now, you imagine a small area surrounding the point P. Electric field at the point is directed outward. You know, positive charge electric field is outward from the charge, right? If you take the normal area is the normal direction. So area vector direction is also along the field direction. Okay. So when you consider the cylinder, you can see through the curved surface of the cylinder, electric field and the area vector are parallel. Angle between them is 0. Okay. Now you look at the flat surfaces here. If you consider a small area on the flat surface, normal is like this. Electric field is in this way along x direction. So this angle is 0, 90 degree. Angle between DA and E is 90 degree. Okay, this you have to keep in your mind. So when you consider the cylindrical surface, you can see that electric field only passes through the curved surface area, curved surface of the cylinder. Through the flat surface of the cylinder, there is no electric field lines. Okay, no electric field line along y direction. So no flux pass through the flat surfaces. You remember this first. Okay. Now we can apply Gauss's theorem. What was the equation for Gauss's law? Phi equals closed integral E dot dA. Closed integral, there is a circle on the integral sign that shows the full area. So we can split the total area into two portions. One is curved surface area and the other is flat surface area. So I am writing curved surface area. E dot dA. It is E dot dA. Dot is there. Plus flat surface area. E dot dA. Okay. And you know A dot B is AB cos theta. We can use that one here. So what will be the phi electric flux? Phi equals closed integral curved surface area E dA cos 0 plus flat surface E dA cos 90. So the second term is 0 because cos 90 is 0. Now we can write phi as, you know, Gauss's law, phi is equal to Q by epsilon 0. So Q by epsilon 0 equals integral curved surface E dA. E is constant, E into dA, integral dA. So what is this integral dA? This integral dA means total surface area of the cylinder, total curved surface area. I told there is, you have to consider curved surface only, right? dA is a small area on the curved surface. So integral dA will be total curved surface area. And you know, curved surface area of a cylinder, what is the equation? 2 pi RL. Okay, so we can write Q by epsilon 0 equals E into what is integral dA? 2 pi RL. Now you can find out the electric field intensity. Q by epsilon 0. Find out electric field intensity. E is equal to, so you rearrange the equation. E is equal to Q by 2 pi RL epsilon 0. And also, you know, the first equation, Q is equal to lambda L in the beginning. Lambda, what is lambda? Linear charge density. So E is equal to lambda L by 2 pi RL epsilon 0. You can cut the L. So what will be the equation for electric field intensity? E equals lambda by 2 pi R epsilon 0. This is the equation for the electric field intensity near the line wire. Okay. In vector notation, we can write E bar equals lambda by 2 pi R epsilon 0 into R hat. What is this R hat? It is a unit vector in the direction of R. So this is how to find the electric field near a line wire of infinite length using Gauss's theorem. Now, if you plot a graph between E and R, you know here, graph between electric field. And distance R. You know from the equation, E is inversely proportional to R. Therefore, the graph will be like this. E, R, what is it? If E inversely proportional to R, the graph shape is like this. Electric field is decreasing with the distance. So graph is like this. Okay. Okay, students. So next application we will do in the next class. Thank you for watching.